the Physics of Sound and Music doc with a review for you of the foundational physics for Chapter U. Now, when we do these foundational reviews with the letters, we go to the text, and you should use your power notes and look at these classes for the multimedia aspects of our class. But we're going to review the basics by going to the downloads and clicking on U, which is the chapter for the spectrogram. So let's look at this. Here we have a spectrogram of a bird. It goes up in pitch, see twice, and then down here 4 times. And to understand spectrograms, we go back to our ADSR from the synthesizer, our shaping of sound. So here we have the attack, decay, sustain, release, and we have a square wave. Now I want to represent the square wave in terms of its sustain. Look at the sustained phase. Let's forget the attack, decay, and the release. Just look at the sustained phase. This is a fixed level of loudness, where I'm going to represent that here with this line. The fixed level of loudness as time goes on. What about the Fourier spectrum for a square wave? Well, if I have frequency here, we have amplitude here, and that gives us the Fourier spectrum. 1 cup of the first harmonic, 1/3 of the third harmonic, and 1/5 of the fifth. Now, when you have amplitude versus time, you usually see the picture of the wave. So you would see the square wave here on the oscilloscope. But here I've emphasized I just want the total loudness. So the total loudness is constant, so it's a straight line in this case. Special diagram to help us understand how the spectrogram works. So when you look at the information in 3D, I have time along the horizontal axis here, left, right, and I have frequency along the vertical, and I have my loudness along this 3rd dimension, which comes out of the page. So this gives me complete information of that square wave. It gives me the spectrum. I have my timbre, I have my spectrum, I have my frequencies, and since I have more than the fundamental, I have the timbre, and I have the amplitude, I have the loudness, and I have time. I have everything. But I want to have it in a book. So what I do is I take the panel that's tall, or say in this 3rd dimension, it's big along this dimension, so this tallness here is reflected in this coming out of the page. I just make that darker. And then here, this is not so dark, and this is lighter. So that's how I get my cake and eat it. This is the spectrogram, which says that I have mostly the fundamental, I have less of the 3rd harmonic, and even less of the 5th. Notice that the 1st harmonic is a certain plateau, and the 3rd harmonic is triple that height. I am missing the 2nd harmonic in a square wave. I'm missing the even, the 4th harmonic. So this is the spectrogram, and if you understand this derivation of the spectrogram, you're all set. This is the basics. You have your frequency against your time. So what is noise? Noise is everything, all the frequencies. What about low frequency noise? Like a sigh. What about a high frequency noise? And all the noise like your ocean. Here are some frequencies. This is doing that Bridge Over the River Kwai, but you have to whistle it because there's only one frequency. Police whistle, the admiring whistle, the I can't whistle, so you just imagine whistling that. You got to be careful with the admiring whistle. It's not politically correct today to just do that. So here we have 2 people who are whistling at each other. They have granted permission for the whistle. I always tell folks they can always whistle. It won't bother me. Here we have the screech owl coming down and going up. Here you have a bird. And in our multimedia section, you get to hear these things, a lot of these, so you should do that. Here is the dog. Ruff, 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 which shows the fundamental and a harmonic, and probably have more harmonics up there. This is just a sketch, and some noise that's in there in the bark. Here is simply just clapping or clipping. This is sort of a clip type of a sound, hammer sound, popping the cork there, something like that. Here is a chord, 3 notes, and that's a train whistle. Here we have a motorcycle, and the noise in the background. Here you have the snake. For the space shuttle, you blast your ears, you have everything. A fighter jet. And notice here for these involving frequency modulations as a siren, notice that when this harmonic here should double, this harmonic that's higher up doubles, it goes up more. See, it's sort of like percentage-wise, if this thing goes up by a certain percentage, but then the other harmonic is double that. So percentage is the same, but if you have 1,000 and go up, you double your money and have 2,000, and 2,000 go 4,000, say. So that's why these things like spread out a little bit more as you go up. This one here is incorrect. So you got this from a text here. This one here, the harmonic should be spaced a little bit more when you go up. They start out here. This is fine here. This is the height, but this is the double the height. But see here, if I double this height, I don't get that. I should be up there. So that one's a little bit inaccurate. But when you do these sketches, sometimes you do with a little poetic license. You do that. Same thing here with the Singer vibrato here. Not as accurate as the real spectrograms that we see in class when we have vibrata. These wiggles here get more pronounced and spaced, the wiggles a little bit more. So see if I'm wiggling here at 1,000 hertz, going up to 100 and down 100. When I'm at 4,000 hertz, I'm going to be going up a tenth, 400 on either side. So once again, poetic license to show the spectrogram in a sketch form. Laughing here, and here the snoring, and woo. Here's a guitar. We put in some white noise, and certain regions are enhanced because of the cavity and the wood and the structure of the guitar. These are called formant regions, the ones that come out enhanced in the spectrogram. Here we have the system of vocal system situation here with the closed pipe with the vocal folds, and the physicists like to idealize things, so that's simply a closed pipe. Straighten it out. There it is, and so much physics can be obtained by this simple model. If you have 15 centimeters for your closed pipe, your wavelength, 1/4 wavelength is fitted to L, so L is 4L, that's the closed pipe rule. Wavelength 60 centimeters, and I can find here the fundamental frequency. 60 centimeters times F is, I have to adjust this to centimeters, so I have 340 and 2 more zeros on there, 34,000 centimeters per second. And I don't know how to divide by 60 without a calculator, so what we'll do is we'll estimate this. This is roughly 500. In other words, 1,500 divided by 3. In other words, you can make this a 35 and make that a 7. You get 500. Or here, if you reduce it, it cancels 0 and have 3,400 over 6. This is 1,700 divided by 2, 1,700 over 3. Add 3 into 1,500, close enough, 1,500. And that is the model of the vocal system, which says that the formant regions will be at the odd harmonics for a closed pipe, and that's where they are. You see those in spectrograms. Enhancements at 500, 1,500, triple, and 2,500. Vocal formants. Well, that pretty much does this chapter here. You should look at your para notes and look at the multimedia things that we have in here to help master these concepts even more. So, and remember, the exam does cover more than just the fundamental foundational physics, which we're reviewing. It does include these other things here. So check out some bird spectrograms here. Go to the birds here and look at some of these here, and go ahead and you click on those and check those out. These are real spectrograms, and these are going to be the accurate spectrogram. So for example, if we look at that Singer, I was talking about that, vibrato there, for example, and if you look at the vibrato, let's go ahead and find some for you here. Let's look at let's see what we got here. We got the spectrograms for, I thought we had some here with the Singer. I think we put them over here. Yeah, here they are. With Crosby here, for example, if we look at some of these, you see the spectrogram is now accurate. See, the wiggles for the vibrato get bigger and bigger here because it's a percentage thing. If you have 1,000 hertz and a percentage is 10%, well, it's not going to be 10%, it's going to be less, but whatever it is, when you take a percentage of a bigger amount, you have more. You're swinging back and forth, so that for these vibrato wiggles get bigger and bigger. Notice that the various levels of the harmonics are always going to be, you know, the center of this is going to be, see if this is a plateau, 1 harmonic, second harmonic is double, then triple, 4, 5, 6, 7, 8, 9 harmonics, but the wiggles will be larger and larger. Very, very nice spectrogram and a great Singer, and check out some of those in the extra credit section. Which means that if you actually answer the questions, you get extra credit. But you should know material in the extra credit section, which is on the para notes.